Yeah. So, okay. So, good day, everyone. Sorry for the unusual delay. So, welcome to the third lecture series, which is on engineering the Guruprasad Prof. So, this is the third of this series. So, Guruda, you can start.
Yeah. So sorry for the interruption. So in our last lecture, actually we discussed sharing secret key in the context of classical world. So from today we are coming to the quantum world, and in quantum world, like Shannon theorem, there is a parallel theorem in quantum, and it is called Schumacher comparisons theorem, possibly discovered in 1995. Here, I'll be telling Schumacher's comparison, which is needed, but I will tell its other implication also. But our main motto is to go towards distilling key and distilling entanglement. Today we will be discussing about distilling secret key, and in our next lecture we will be discussing distilling entanglement, which also implies distillation of secret key. Now come to Schumacher's comparison. So consider a source which produces a state phi k with probability pk, and it may be the case that phi k are not a orthogonal set. And if you consider a particle randomly from this source, then its density matrix is given by this quantity, summation over pk phi k phi k. Now if you collect n qubits, I am restricting myself to qubits from the source, then you can tell the state is rho tensor n. That means rho tensor, rho tensor, rho tensor. But at the same time, you know that rho have many decomposition, and all the decomposition are actually equivalent. If not, then you can use it to signal. That's why all the representation of a given rho are actually equivalent. So what you can do, you can take the spectral representation of the same rho, where if you take spectral representation of a qubit state, then there will be only two terms. So it is summation over Tm, psi m, where psi1, psi2 are orthogonal, and T1, T2 are probability, and T1 plus T2 is equal to 1. Now, instead of thinking that the source is phi k pk, you can think that your source is psi m, Tm, psi m, or psi m, Tm. That means with Tm probability, psi m is coming from the source. These two sources are equivalent. So you can analyze everything in terms of this spectral representation. That means in considering this as if the source is Tm psi m. Now from Shannon theorem, once this psi 1 and psi 2 being orthogonal, they are like 0, 1 bits. So number of typical sequences which have already studied in Shannon's theorem, this is nothing but number of orthogonal states will be 2 to the power n into 8 HTM, and space, typical subspace spanned by these typical sequences will be 2 to the power n HTM. The sequence being orthogonal states, as I told you, they span the subspace of dimension this. So actually you can think that whatever string comes, they will be restricted in this typical subspace of the total Hilbert space. And you know this thing that this is nothing but 2 to the power n into S rho. And in particular, you know that this HTM, this will be less than equal to HPK. That means S rho will be less than equal to HPK. Now, let P be the projector. Now we consider the subspace, typical subspace, whose dimension is this for n qubits, and let P be the projector on this typical subspace. Then it has been shown, it can be shown that if you take rho tensor n, P, and take its trace, then it is almost equal to 1. That means it is actually, not less than equal to, even you can show it, it is greater than, strictly greater than 1 minus epsilon. Now question is how to send quantum information. Again, I am mentioning that our motto in this talk is not sending quantum information, but because I am discussing Schumacher's compression theorem, that's why I am telling what is meant by sending quantum information in the context of Schumacher's compression. Now, you can think that from the source, that sequence of states that is coming, that are like this, because we are thinking that this source is this, Shannon. So if you collect that all the typical sequences, they will be of this kind, where the total number of typical sequences will be 2 to the power n into s rho. Now, what you can do, if you want to send these sequences, you see there is what is the number 2 to the power n into s rho. So what you can do, if you want to send this information, instead of sending n, because they are encoded, still they are the n qubits. They are n qubits. But why to send this information of this sequence, why do you spend this n number of qubits? You can compress it. You define a unitary operator which acting on psi I, give you psi I compressed. That means the psi I compressed, it consists of n into s rho number of qubits, and all the rest of the qubits n into 1 minus s rho, they become 0. So you can apply this unitary transformation. Now you can tell that my actual sequence, it may happen that my actual sequences will consist of a series of phi k. I mean, you are collecting from this source. So what you can do, you can take any of the say phi j has come to you. Maybe the actual source is this. So if you collect qubits from this thing, there will be phi 1, phi 2, phi 5, phi 17, something like that. So whatever it comes, what you do, you take the actual sequence and you perform this measurement. That means you perform a measurement which either projects on typical subspace or is in its complement subspace. Now there is a high probability that it will be projected in the typical subspace. So the state will somehow change. It will be psi typical, but already you know psi typical is spanned by this psi 1, psi 2 up to psi 2 to the power n s rho. It is spanned by this thing. So this psi typical can be expressed as Ci for psi I. Then what you do, on this psi typical j, you apply your u. You apply your unitary operation, which actually will discard n into 1 minus s rho number of qubits. Still, it would contain the actual quantum information. Then I have not written, but then this, now it consists of how many qubits? N into s rho qubits. You send it to your friend. What your friend will do, your friend will take n into 1 minus s rho number of n into 1 minus s rho number of qubits in 0 state and apply u inverse. Then he will get the original sequence.
Sir,
Now,
I have a question here. Yeah. So I'm saying this unitary, does it require the knowledge of this psi 1, psi 2 at least?
No. Only knowledge it is rho.
Which is spectral?
Rho.
Exactly.
If you have information of rho, then from its spectral representation you will get it.
So that's why I'm saying at least the spectral knowledge
Gives everything. Gives everything.
Exactly.
So you don't care whether actual source is this, is something else, because rho has infinite possible decomposition. Whatever decomposition it will be, it may be, but I don't care.
So I mean, suppose I took another state which is rho prime, and that is from another source whose spectral decomposition or spectral eigenvalues are different. Then I need to change my unitary.
Yeah, it depends on this spectral. It depends only on a spectral.
Okay. Now I'm just a little bit confused.
Because
So because
yes,
the spectrals are orthogonal. Okay.
yeah,
So suppose your unitary actually depends on those orthogonal states.
yes. But you see, when let the source is different. So the sequence that is coming is this, where these states are not orthogonal. And their number may be many. But for a spectral dimension, there will be only two terms. But for another decomposition, there may be many terms. But whatever it comes, I will perform this measurement first, so that it is projected in the typical subspace. Once it is projected in the typical subspace, now it can be written as Ci psi I, summation over Ci psi I, where these psi i's are orthogonal in the typical subspace. It is a orthogonal basis in the typical subspace.
Yes. I mean, suppose if I don't have any knowledge about the source.
Yeah.
Suppose if I don't have
But
any knowledge.
Rho I know. Rho is known.
So at least that information is required. At least I need the row informations.
Yeah.
Otherwise, I cannot use it as a computation.
No. Otherwise, everything is random. You cannot do anything.
Agreed. Yeah. Okay. Thank you, sir.
So whatever decomposition is the source has, it does not matter. If I have the knowledge row, I can mechanically perform this operation. I will take whatever comes, I will make this measurement with high probability. I will project it in the typical subspace. Then you apply this U, which discards n into 1 minus s to qubits, send it to your friend. Your friend will take n into 1 minus s to number of qubits in 0 state, apply U inverse, and you will get the exact quantum state. Now it has a nice application. Yes, any question?
Yeah, this measurement is entanglement measurement.
It may be. But so what I am telling that it is projected on the typical subspace.
Yeah, that I understand. But I'm saying then practically, if it is entanglement basis measurement,
possibly.
Then practically I have to wait for the all n qubit. I cannot do by one.
Yeah.
Yes.
So this P, see money. This P is projected on n qubits.
Yes.
On n qubits, but not the n qubits whole space, on the typical subspace.
Typical subspace, yes. That's why it is a highly entangled measurement. I have to wait for the all n qubit, and then I have to perform this measurement.
I think, can you hear me?
Yeah, Manav.
Actually, yes. So this typical subspace, although it looks like entangled, but it's kind of a identity kind of operator on that subspace, no? Ideally, you can even decompose it into, that means this in this identity space, that means this projected space, I can come up with many bases to form this identity, no? So in principle, actually, you can even come up with non-entangled measurement.
It may also happen.
Yes.
But okay, it may or may not, but it is not important in this case, what I am discussing. Because my measurement is P identity minus P is equal to identity. When it will collapse on P subspace, then only I will keep the result, and it is typical. Then I will apply U on it and send it to my friend, which consists of n into s row number of qubits instead of n qubits. But still it will convey. So my next example will tell you exactly how it carries quantum information. So already you know that if you start from a non-maximally entangled state with n copy, which is A00 plus B11 with n copies, then you know that if S row A, you can calculate the marginal density matrix rho A, then you know from these n copies, you can create maximally entangled state with n into S of rho A copies. N into von Neumann entropy of the marginal density matrix of one of them. Now, this process is reversible. Actually, starting from n into S rho A number of maximally entangled state, you can create n number of non-maximally entangled state. How to do this? So this is Alice's lab, this is Bob's lab. What Alice do? Alice creates n qubits in these states, in this non-maximally entangled state. Alice creates n number of non-maximally entangled state in her lab. Okay. Then what she do on this side of the QB of all these non-maximally entangled state, we will take all these qubits and apply the compression. That means compression means we will measure its P identity minus P. This measurement she will perform and then apply this unitary operator and discards n into 1 minus 1 S-row qubits. So finally, she will get up all these qubits on this side, they will be compressed to n into S-row a number of qubits. Now already they are sharing n into S-row a number of maximally entangled states. So what they can do 1 by 1 teleportation. Perfectly, they can teleport this n into S-row a number of qubits because already they are sharing that number of maximally entangled states. Now Bob will do? Bob will take n into 1 minus S-row a number of qubits in 0 state, apply U inverse and get the n qubits. So finally, they will get this A00 plus B11 states whose number is A. That C is compression, D is decompression. Or more pictorially, you can see Alice prepares a number of non-maximally entangled states. It is a step by step, and they are sharing this thing. Then apply compression. So after compression, this number and number of maximally entangled states, this number become same. Then teleport 1 by 1. Then this side it is n qubits, this side it is n into S-row a number of qubits. Then after decompression operation, both of them will hold n number of qubits, and this n number of non-maximally entangled state will be produced. So this shows that actually this Schumacher compression, this keeps the quantum information intact. Anyway, but today we are more interested in a different problem. Today we are interested in a problem where the source is known. It is phi k pk, where phi k in general may not be orthogonal. Now, if you consider the typical sequences, then if you collect qubits from here, then sequences, the typical sequences means sequences with P1 into n number of phi 1, P into n number of phi 2, P3 into n number of phi 3. In this way, you will get a sequence like this, which I have renamed as phi j, where j is equal to 1, 2 up to 2 to the power nh pk. Now, question is how many of them can be identified? This is a different question. Now I know the source. I am collecting the particle. The string may be any one of these 2 to the power nh pk. I want to know it. In general, it cannot be known. That's why I am asking how many of them can be identified. Here the answer is the following. If we randomly choose 2 to the power n into S row numbers of strings out of 2 to the power nh pk, then there is some POVM measurement by which the sequence can be identified with probability very close to 1. That means there are how many possible sequences are there? 2 to the power n hpk. You cannot identify them. But if you randomly choose less number of them, that is, if you randomly choose 2 to the power n into S row numbers of strings, then there is a measurement, POVM measurement, by which you can almost reliably identify this sequence. But I am considering the same thing in a more general setting, which is called HSW theorem. Instead of taking pure state, I am now considering mixed state. That is unnecessarily aligned. Now the source is rho x px, where rho x in general is not a pure state. Again, you can calculate rho, which is nothing but summation over px rho x. Now, with the aim of knowing classical information, classical information x, by here x is classical information, by some process of quantum operation, let one gets the output 1. Let someone is trying to get the information of x by doing some Yogian measurements, and let his output is y. Then it has been shown by first Holebo, then Schumacher, Westmoreland, that this mutual information is bounded by this quantity, which is called Holebo quantity. That means mutual information between x and y. That means information of x that can be derived from y cannot exceed this by this quantity, which is S rho minus summation over px S rho x. And this quantity is called Holebo quantity. Now, what is the meaning of this thing? Because we have to use it for a source which produces n qubits. So, if I again consider that possible typical sequences collected from here, again I am telling it is known source. It is known source. Possible typical sequence of states are like this. Now, question is, how many typical sequences are there? Again, the answer is this. These many typical sequences are there that contain n into px1 number of rho x1, n into px2 number of rho x2 in this way. Now we are asking the same question. How many of them can be distinguished? Now the number is 2 to the power n into Holebo quantity. Now let us try to we are not going to prove this thing because proving this thing is a little bit difficult. But at least we can convince ourselves that this may be the answer. A necessary condition towards this answer, let us find a necessary condition towards this answer. Now, finally, what is the dimension of the typical subspace? Again, from Shannon thing, because ultimately what is collected from this source is rho tensor, rho tensor, rho tensor, rho tensor up to n terms. So, dimension of the typical subspace already from Schumacher's compression theorem, we know it is 2 to the power s rho.
Is it 2 to the power s rho or n s rho?
Oh, again, there is a mistake. N s rho. Thank you, mate. N s rho.
It's a,
let me tell one thing. I will correct it because already in words I have typed everything. So it is very trivial for me to correct this thing. You don't tell others. I will do it in 2-3 days and I will send you. Okay, mate?
okay, sir.
I will correct it. Now, here the typical sequences, all these typical sequences, they don't have one-dimensional, they are not one-dimensional. Because here it is density matrix. So they are also concentrated in a subspace. So what is the dimension? What is the dimension of the typical subspace of the sequences of states? You consider any one of them. So already you know they are in a typical typical sequences, there will be n into px number of rho x1, n into px2 number of rho x2, n into px3 number of rho x3. So for n into px number of rho x1, it has a typical subspace dimension which is 2 to the power n into okay, it is n into px1, sorry, n into px1 into s of rho x1 into for the because there will be n px2 number of rho x2 is the typical subspace dimension will be this. Similarly, for the third term, it is this. For the third rho x3 state, it is this. In this way, it will be this. So finally, it is like this. 2 to the power n into summation over I, pxi, s of rho xi.
So, sir, basically,
so that means each string has a subspace, which is, and all these strings have this property, no? npx number of rho x1, np into npx2 number of rho x2. This is true for every string. So every string will have a dimension, typical dimension, which is equal to this quantity. Tell me what are you telling?
So I'm saying this 2 to the power n sum over p I p. This is the conditional entropy, right? N
No. Yeah, I am telling
I
that
get it.
if you consider a string, it has a typical subspace dimension. I am calculating that dimension.
But that would be equal to, sir, the conditional entropy. Given x, what is the uncertainty of? I mean,
Okay, but
yeah.
here you try to be simple.
Yes.
I am trying to tell that each string has a typical subspace dimension which is equal to this.
Yes. Okay.
Now already this every string has a dimension, subspace dimension, and total typical dimension is 2 to the power ns rho. So then the maximum number that you can discriminate between these among these string that cannot exceed this quantity. So you have to divide by this quantity. I mean, volume subspace of these typical sequences. You have to divide by this quantity. So this is the maximum number that you can distinguish among these strings of mixed states, and which is nothing but finally it is 2 to the power n into x whole over quantity of rho. So that's why I was telling that the answer is this thing, but it is very difficult to show this thing because you have to consider a POBM which will try to distinguish among these things. And
hello, sir.
Yes.
Yeah, I have a question. Like you said that this many sequences discriminated.
This may be.
So
I'm telling you, it is a necessary condition.
Okay. So is it related to Hellstrom bound? Like
no. Here you can trying to identify the thing conclusively.
Okay.
It is not with Hellstrom. So I'm telling this is a necessary condition, but it has been shown that you can choose a POBM to identify this string, and that POBM looks a little bit weird, but still they cannot prove it directly. They show that if you apply this POBM to identify this string, then there is an error, and finally they calculate the average error, and then they show that for n large, that error tends to 0. In this way, they can prove it. That you can read from Nielsen Chuang or Mars Wiley's book. So now let us see the same thing pictorially. So how many typical sequences are there? Typical strings are there. If you collect from this thing, if you collect from this known source, then that number is 2 to the power n into HPX. And what is the number that you can identify? If they are selected randomly, that number is 2 to the power n into this whole over quantity. So out of these sequences, if one randomly choose 2 to the power n into whole over quantity number of sequences of states, which is called HSW code, there is a POBM measurement that can reliably distinguish among them. So this is the total number of strings, and among them, if you choose randomly 2 to the power n into xi rho, then you can identify them. And actually, they can be selected in so many ways. So if the string belongs to one of the boxes, then they can be identified. But for that, it has to be inside one of the boxes. So these are called HS code, HSW code. HSW code means those things can be discriminated by some POBM measurements. So out of these sequences, if one randomly chooses a number of sequences of a state, which is called HSW code, there is a POBM measurement that can reliably distinguish them. So all of these are called HSW code. That you have to remember. Now towards privacy amplification, again I am discussing something which is which is not practical, like we discussed in our Shannon case also. So basic idea of by a simple example, you consider 4 states, 0, 0, 0, 1, plus and minus. If you take equal mixture of them, then this is identity by 2. But I am trying to tell you that even if you may consider some subsets, some subset of these states, then also they can be equal to the density matrix. Here it is trivially true. You see, all these 4, if you take them with equal probability, it is identity by 2. But instead of that, if you take 0 and 1 with equal probability, it is also identity by 2. Similarly, if you take plus and minus with equal probability, again it is identity by 2. And this can be used for privacy. How? Again, I am considering a very idealistic case. Let the message is 00011011. This is classical message. And they are encoded in this quantum state A1, A2, A3, A4, which is orthogonal. These A1, A2, A3, A4 are orthogonal state. And when Alice sends this quantum state to Bob, it perfectly goes to Bob. That means if Alice sends A1, what A1 reaches to Bob. When Alice sends A2, A2 reaches to Bob. But when Alice sends A1, 0, what state reaches to Eve is 0. When Alice sends A2, what state reaches to Eve is 1. When Alice sends A3, what the state that reaches to Eve is plus. And for A4, it is minus. Now you see, this is very idealistic. This is not at all practical. But now you can see that it can be used for sending secrecy. Actually, Alice can send 2 bits of information as AIs are orthogonal. But Alice can generate 1 bit of secrecy with Bob. How? She encodes 0 with equal mixture of A1, A2. And name it as row 0. And for 1, she encodes this in equal mixture of A2, A3 and A4 and name it row 1. That means Alice sends either row 0 or row 1 to Bob. And what Eve receives for 0, Eve receives, if you remember this correspondence, then what Eve receives for 0 bits, Eve receives equal mixture of 0, 1, which is identity by 2, for when the information is 1, when the bit is 1, what Eve receives is equal mixture of plus and minus, again identity by 2. So these two cannot be discriminated. That's why Bob gets 1 bit of secrecy and Eve gets nothing. I think it is clear. This technique will be used now for a general case, for a practical case. Just a minute. I have forgot to bring a water bottle. I'm just bringing and starting. Just wait a minute.
Okay.
Yeah. Now we are coming to a covering theorem, which is actually dual of the HSW theorem. So again, we will go to the source. If you go to the source, then how many? There will be 2 to the power n into HPX number of sequences of states, and if you add them, and they will come with equal probability with this probability, they are actually is equal to the same state, row tensor n. Now, dual of HSW theorem implies that in the above summation, how many terms are there? 2 to the power n into HPX number of terms. Dual of H's theorem implies that in the above summation, if one choose 2 to the power n into this whole quantity, this number of sequences of states randomly, then also if you take them with equal probability, and this probability will be like this, then again it is same state. So if you consider a subset from this, all these string in a random way, and the number is 2 to the power n into chi-rho, then again they also, their equal mixture also creates the same state. Hence, in some context, HSW code can also act as privacy amplification set. So you see, it is some what I am. So I have told that if you know that your string has come from one of these things, then you can discriminate among the. If the string come, if the box is known, then you can discriminate among these points. And why I am telling, because HSW theorem has identified the highest number of strings that can be identified. That's why all these boxes are equivalent. All these boxes are equivalent. If they are not equivalent, then actually maybe more number of strings may be identified. That's why I have no proof. It has been proved in Marx-White, but I intuitively try to understand, because all these HSW code are equivalent. That's why they themselves, among themselves, that they cannot be discriminated. That's why all of them, if you take this Pointsman sequence of states, if you take all these states with equal probability, then all these HSW code are actually produces the same state, rho to the power rho tensor n. So it is some kind of dual of HSW theorem. It is called covaric theorem. Earlier one is called packing theorem. It is called covaric theorem. But as I told you, HSW code can be used in some context as privacy amplification set. So the same set, all of them are rho tensor n. So all of them. So if you don't tell if the number of the boxes, then all boxes are equal to E. That technique will be used in deriving secrecy. The sets cannot be distinguished as they represent the same density matrix. I think up to this point it is clear. Now coming to secret key distillation. So consider a state rho AB, and sometimes a direction has to be given, because S rho A minus S rho AB also can be calculated. But here I am taking, I see current information for rho AB in some direction in this way, which is S rho B minus S rho AB. This is called current information of the state, and I am taking a state rho AB in such a way that this is non-zero. Now, if you take the purification of this state, this is psi AB, ABE, where E may be the eavesdropper. Now, if you take the spectral representation of this state in the A versus B curve, you will be very careful. I am taking a spectral representation because this is three-party system. That's why I am taking my spectral representation in a particular way. In which way? A versus B curve. Then it is
Spectral means Smith decomposition.
oh, this is again there is a wrong. Smith decomposition. Yeah, it is Smith decomposition in the A versus B curve. So it is something like this, and I have taken again AB system to be qubits. So it is, there will be two terms, X, and for B I have not taken anything. So it is psi X B. It is pure state. And for every psi X, you can calculate marginal density for B as well as marginal density matrix of E, and the whole of rho B will be P summation over Px rho Bx, and rho is Px rho Bx, rho Ex. And also you can calculate this quantity, whole level quantity, this similarly whole level quantity for X versus E. This is this. And if you calculate the difference between these two whole level quantity, that means whole level quantity between Alice Bob and whole level minus whole level quantity between Alice E, it is this quantity. Now I am asking students, can you tell me from this step how this step comes? Any student, can you answer me? That means I am trying to tell summation over Pxs rho Bx is equal to summation over Pxs rho Ex. Why it is true? You should be very careful because this rho Bx and rho Ex is coming from a pure state. That's why these two quantities are same. So they cancel. Finally, it is rho S of rho B minus S of rho E. And S of rho E is nothing but S of rho AB. Because rho AB is a pure state. So if this quantity, if current information is strictly greater than 0, it implies that whole level quantity between Alice and Bob is strictly greater than whole level quantity between Alice and Eve. Now what you do, you take n copies of the state.
Guruda.
Yes.
So in the previous one, so obviously a whole level quantity has something to do with like classical capacity of a quantum channel, no?
Yes.
So here, if you go to the pure state you have considered, so can you go to the previous slide?
Yeah.
So the state you have considered is not a classical quantum state, or you started with classical quantum state?
No. I have started with the quantum state one. After measurement, it may be classical quantum seeking.
So
But initially, it is rho AB.
you have considered X you have considered in this purified state, for example.
Yeah.
So this is like the classical information that you want to send after encoding it into psi X or somewhere.
Yeah, it as X are orthogonal, so it is like bits. But still, I am working in the quantum setting. But after the measurement, you will get only classical information. You will perform the measurement on A. That I'll be doing just now.
Okay, another point in the next, it's quite tempting for me to see, because this is exactly also this coherent information has something to do with the quantum capacity of quantum channel, no? So that means it is.
Yes.
So that means it is again has something to do with like this quantum privacy.
Yeah. Today we will connect it to the privacy. Tomorrow, next in my next lecture, I will connect it to entanglement.
Okay. Thank you.
Actually, all these talks are prepared to tell the main thing in the fourth lecture. Can I proceed?
Please, thank you so much.
So consider the n copies of these states, this same state. So you can tell that so many copies you have taken. So there you will get sequence of 0 1s. So xn, where xn is the sequence of 0 1. So you can write them in this fashion. This xn is sequence of 0 1. The number of HSW code for B is the number of HS. So xn is sequence of 0 1. So how many if you consider this source as, because if you measure you will get xn with probability pxn. So if you consider the Shannon information of this thing, this is nothing but 2 to the power n hx, and it is Shannon because it is classical. So now I am asking what is the number of HSW code for B? It is 2 to the power NHX by 2 to the power N I Alice versus Bob. It is something like this. It is the total number. Among these, how many boxes are there? Each box contains 2 to the power N into X row, whole quantity. So instead of writing whole quantity, there I have written this in terms of mutual information. So how many HSW codes are there? This is the number. And name them as L is equal to 1, 2, 3 up to L, where final L will be, this is conditional entropy, to the power NH XP. And you know already that Bob can distinguish the sequence of states which is contained in a particular L. If L is known, then the states that is contained by L can be discriminated, which already we have discussed in our HSW theorem. And the number of privacy amplification sets for E, because size of HSW code and size of amplification, size of the amplification sets, they are actually equal. But when I am considering HSW code, I am considering it for B. And when I am considering privacy amplification set, I am considering for E. But both have this same form of the size. It is also 2 to the power N into I XB. It is also 2 to the power N into IXC. So this number is this. And also the total number will be 2 to the power N HXC given E. And name them as S is equal to 1, 2, 3 up to 2 to the power N into H X given E. Now, again, maybe this is a repetition. If you consider any of this set and take the collection of all these states that is contained in a particular privacy amplification set S and take them with equal probability 1 by S, it produces the same state for E. It produces the same state for E. Now, the number of privacy amplification set in each HSW, because already you know this IXB and IXC, to consider them, IXB is greater than IXC. So, number of privacy amplification sets that is contained in a particular HSW code, because size of the HSW code is this and size of the amplification set is this. So what is the number that is contained in a HSW code? What is the number of privacy amplification set that is contained in a HSW code? This is given by this quantity. And already you have seen this quantity to be equal to some current information. And again, that will come later. Name them as M is equal to 1, 2, 3, 4 up to M, where M is equal to 2 to the power N into identity X B minus, mutual information between XB minus mutual information between XC. Here the mutual information in terms of Holebo-Westmoreland Schumacher's theorem. Now you can check that total L into M into N, this is total number of possible sequences 2 to the power N Hx. So the full picture is total number, just a minute. Yeah. So total number of sequences is 2 to the power N Hx. Now you can subdivide them by this HSW code. L is equal to 1 is a HSW code, L is equal to 2 is a HSW code. And this L is equal to 3, that is 2 HSW code. And each HSW code has how many points? 2 to the power N into IXB. Now each HSW code contains privacy amplification set, which is M is equal to 1, m is equal to 2, m is equal to 3 in this way. And each privacy amplification set contains 2 to the power n into I xc number of points. And already you know it is privacy amplification set. So if you consider all these states with equal probability, they produce the same state, because that is the property of the privacy application set, that all of them are equal. Now, in our case, we are only considering it for E. But this is a general result. That's why I was trying to tell that HSW code and privacy amplification set has the same size. But in our case, as Holebo quantity of between Alice Bob is greater than Holebo quantity of Alice Eve, so we're exploiting this thing, and we are using this idea of privacy amplification set for E. And HSW code, where the state can be discriminated, we are using it for Bob. Now already you know the state is this, your state is this. So what you do, on each qubit you measure in the 0-1 basis. On each qubit you measure in the 0-1 basis. So most likely you will collapse on a typical sequences. So I have written those typical sequences, because if you consider this picture, you will collapse on a point, and every point will have a number L, will have a number M, as well as will have a number of S. So by L, M, S, you can identify each sequence of 0, typical sequence of 0 and 1. Because total LMN, you see, L into Mn into N is equal to 2 to the power NHX, which means it is the total number of typical sequences of 0, 1. So you will collapse on some typical sequences, and because of correlation for Bob and Deep, it will be some high LMS, where LMS sum to, here the sum means L is equal to 1 to capital L, M is equal to 1 to capital M, S is equal to 1 to capital S. And this is the total number. Here actually you can write L into M into S. Now for my, it has not been done in the discussions made by Rebecca Quinter or Mark Wild. But for my purpose, I have swapped this state to separate register. This state XLMS, because there are huge number of L is equal to 1 to L, M is separately, M is equal to 1 to M, S is equal to 1S. So I have taken them by swapping to a separate register. L for A1 register it is L, A2 register it is M, for A3 register it is S. So I can write the whole state in this way. For this side I didn't do anything, but this side, for S side, I have taken, because of this space, I have not put a tensor product symbol here and here. So just I have taken this state in 3 separate registers. Now Alice has performed the measurement and the sequences he has seen, so it knows that in which L in which HSW code it belongs to. That means he knows the number L, so he will announce the number L. So value of L is announced, and Alice throws out A3. So after announcing, again I have made some mistake. After announcing L, this register is not necessary. So again I have written it wrongly. Alice throws A1. Oh no. Alice throws A1 and A3 also. Because A3, at least for this purpose, Alice does not need. So we will take trace over A3. So when L is known, then let L is equal to, say, L has collapsed on L0. So I could have written here L0MS, L0MS, but L has been fixed. That's why I have not used L. Because already this L has been announced. And for Alice, this A3 register is not known. He will take S over S. So he will throw out A1 and also throw out A3. So final state will be psi A2 B is equal to 1 by MS, summation over MS is equal to 1 to MS, MM for A2, tensor psi MS for Bob and B. I think up to this point it is clear. Yeah. Now, so for a given L, how many points are there? Again, I have made some mistake. It is LMS. It is LMS because it is S. So it is LMS is equal to 2 to the power HN. So what I am trying to convince you that Bob makes the following measurement and extract the value of MS. Because Bob, once L is known, Bob can discriminate all the points contained in a particular HSW code, which may be L is equal to 1, L is equal to 2, L is equal to 16. But L has been already announced. So the information of M and S can be extracted by Bob. So what Bob does, Bob takes some extra register B1 in a state 0 and apply unitary acting on B1B, which gives, actually Bob could extract M information of M as well as S, but he doesn't need the information of S. Only he is recording in a register B1 information about M. But actually when L is known, actually Bob could extract information of M and as well as S. But he is not registering the information of S. He is only registering the information of M in a separate.
Just
Yeah.
the earlier slide.
This
figure. The picture you have shown, no, this bigger picture. L. So when L is known, Bob can know everything within a box.
Yes. That means M into S number of points.
Yes, that means he knows identity of M as well as S.
Identity of S.
On the other hand, when L is known, Bob can only know S, not M. No.
No, if information of M is given to if, then actually these are for if this is also HSW code.
Exactly. That's why given the L, Bob if can only know S, not M.
Yes.
So
And you see M is not being announced. Bob is extracting the value of M.
I see. And since Bob knows that okay, S if can know, they are not using the S. That's your trying to say.
Yeah.
Okay.
So now you see. Yeah. So Alice is extracting the Alice actually could extract the value of M and both, and that will be needed in entanglement distillation. But in this case, actually Bob does not need the information about S, though he can extract the value of S. But with a register B1, he is only recording M, not S, because he does not need it. So ignoring Bob's system B for the state ATO, the state of Eve is the following. Now you come to Eve. What is the state of Eve? For a given MS, state of Eve is this. Now remember the idea of privacy amplification set. For all M, let M is equal to 1. Let M is equal to 1. Let M is equal to 1. because L has been announced, and let L is equal to 17. Let L is equal to 17 and M is equal to 1. Now, problem of Bob, the problem of Eve is that if he has no information about M, all the states are equally probable to him, and this thing, because this is the privacy amplification set, this is equal to the state of if rho E tensor N. And similarly, when M is equal to 2, again, this is rho E tensor N. When M is equal to M, and when M is equal to capital M, this is also true. So all these M is equal to 1. After L is given, M is equal to 1, M is equal to 2, M is equal to 3, up to M is equal to 2 to the power, M is equal to 2 to the power this number, they are all equivalent to E. So you remember this thing, that all these privacy amplification sets are actually equivalent to E. So the Bob also ignores that. Now Bob also ignores the B system. Bob also ignores the B system. Where is B system? Yeah, B system is here. B system is here. Because he has already taken the information of M in B1. And it remains. And now you ignore B. So the state finally you are given. So this is this, and you should also be very careful that after this measurement, I am writing psi. That means I am writing a density matrix, not a pure state. Though I am writing the same symbol, actually I am not giving the case sign. That's why it is actually after this step, after this measurement on this state, I have taken all of them are density matrix, but I am using the same symbol. Yeah. So after Bob ignores this B system, what remains? It is 1 by M, M with A2, M with B1, and for now this summation, it was summation over MS. Now on this thing, there is the meaning of summation of S. So summation of S, you can take it inside. So 1 by S, summation over S, you can take inside. And you know, for a given M, all of them is equal to rho E tensor N. So finally, using covering theorem, we get the density matrix between Alice, Bob, and Deep is this. That means a nice key is shared between Alice and Bob. What is the value of M? It is 2 to the power N into that. That means this much secrecy. N into this much secrecy per, that means per state, this much secrecy. Identity XB minus XC can be derived from each state. So Alice and Bob is holding this secrecy and Eve has no information. So successful sharing of secrecy, which is equal to current information of the state. And so Alice and Bob are happy sharing this secrecy, and Eve is little bit angry because he didn't get any information about him. That's all in this lecture.
Okay, sir, I have just one question, one clarifications. Maybe somehow I missed it. So so this coherent information, if there is a coherent information which is greater than 0, so that means the whole above information difference is greater than 0, then surely we can get some secrecy.
Yeah.
But is this the optimal?
Oh, that we don't know. You cannot tell because you see,
Okay.
From bound entanglement, you can derive secrecy.
And
because
the other way around,
current information of a bound entanglement state, I mean PVT bound entanglement state, it is 0.
Yes, good. Okay.
So I am not telling this is the best way. to even derive secrecy. But at least the amount which is equal to coherent information, at least that amount per state can be derived.
So the statement would be the coherent greater than coherent information
Greater than equal to this.
greater than 0 is a sufficient condition for secrecy, but it is not necessary.
Because you see, this is very particular kind of thing. You are taking the whatever psi AB, you are taking its speed representation in the A versus B in this form, and then you are performing your protocol. So this may not be the best way to do things.
Exactly.
But it is nice that I can use all these things that we have learned.
Yes.
But Kuruda, this coherent information can be used to kind of say that this is the guaranteed privacy that I can acquire or something.
Not only that, actually, by just one-way communication, you can derive this secrecy. Because only in this protocol, Alice has sent the information of L. Just that. After that, there is no need of communication. So it is one-way communication from Alice to Bob.
Yes.
So both-way communication may give better secrecy rate.
So in case of both way, so what information Bob will send to Alice?
Yes, so repeat your question.
So when you say both way communication.
No, I am not. I have the protocol immediately. But I am trying to tell that both way you may be, because what you can do, if you use both way LOCC, then maybe you may be able to extract more entangled state than this coherent information. And once you distill more entangled state, then you can use it for privacy.
Okay. Yeah.
I just one statement. Yeah.
And let me be more clear. You can, Mano. You may consider some Warner state whose coherent information is 0, but still it is entangled. Now, using both way LOCC, you can extract maximally entangled state out of it. And if you have maximally entangled state, you have secrecy.
Okay. Yeah. So in some way it kind of gives you a kind of a lower bound, no? So that much
it is a lower
minimum
bound.
you should have. Yeah.
So I think, Guruda, you can say this example, no? If you take the W state, you can give this example. If you take the W state,
Yes.
So look into row AB and row AE are identical, no?
Yeah.
So that means one way you cannot distill it.
Yes.
But all 2 qubit states are distillable. So with Bob help, the backward communication, you can distill.
Yeah, this is the best example. Yeah.
Good. Yes, right.
But I have one question. I'm saying here, I'm saying physics-wise.
Yeah.
As we have learned from second lecture, that in classical world there is no physics which can guarantee this coherent information is greater than non-zero.
Yeah.
So
or mutual information between AB is strictly greater than mutual information between.
Exactly. This is the step. Precise step. But here now today you give a protocol where you show that it is actually due to this entanglement or some quantum behavior.
Yeah.
We guaranteeing that this is actually non-zero. On the other hand, in the first lecture you have also shown that for PPT entangled state also we can get secrecy. Probably you have discussed that is a non-zero rate, zero rate, but probably non-zero rate also possible.
Yeah.
So I think
non-zero rate we got it, money. In a
non-zero rate
bound entangled state.
Yeah. So now my question is, in today's lecture, this discussion, what physics and in PPT entangled state, what physics is playing there?
Today actually this is a manifestation of some kind of monogamy, because when coherent information is non-zero, then you are sure that this hollow quantity between Alice and Bob and Alice and Eve, they are different, and between Alice and Eve, it is surely less than Alice and Bob.
And in PPT entangled case?
PPT entangled case, I don't know how to express it, but that is also true. But maybe they are in the protocol. I don't know whether we have used two-way protocol or something. That I don't exactly remember. You have to see
I see.
whether two-way protocol you have applied.
But sir, can I say this way, that if coherent information is greater than 0, this implies that the Hollow informations between Alice Bob greater than equal to Hollow informations between Alice Child.
Yeah. For Alice it is, and for Alice it is classical information.
For Alice it is classical information.
Yeah.
But on the other hand, it is not necessarily sufficient.
Yeah.
So, and for the PPT states, actually it is happening that the Hollow information between Alice Bob, it is greater than 0 still.
Yeah.
For the PPT entangled state.
Though quantum information is 0.
Though quantum information is, coherent information is.
You remember that has been constructed in a peculiar way. You have taken another system A1, B1.
Exactly.
So
The shielding state. Shielding state kind of concept.
Shielding kind of things have been used.
Maybe Guruda, it can be interpreted also in this way, no? That when your coherent information is negative,
yes,
what
information is negative.
Correct.
That means it is may be negative. Yeah, then
yes. So in this particular case, Eve is in the upper hand. That means Eve will have rather some access to privacy rather than Bob.
Yeah. If Alice and Eve cooperates.
Yes. Yes.
If Alice agrees to cooperate with Eve.
So it's kind of a monogamy kind of thing, no?
Yeah.
Okay.
Manik gave the nice example. W state is the best example today.
Correct. But anyway, so this entanglement distillation part you have mentioned in the early stage.
Yeah.
I think this is also something to do with this decoupling, no?
Yeah. Decoupling it.
This is exactly.
But
decoupling
it needs more operation and more careful steps. Because you know that then there you have to keep the coherency intact. You cannot make you cannot do measurement, but it is incomplete measurement so that coherency may be maintained or entanglement may be maintained. But finally also you want to separate out it.
Correct.
So it will be a little bit involved protocol.
Yes. There you more on the level of like isometries and all. Okay.
Can you just go to that slide where you discuss this HSW theorem is reversible, that part?
Yeah, this one?
No, a little bit back. Earlier, third or fourth.
Oh.
Yeah, this one. The earlier one, yeah. Next one. The picture. Yeah, this one. Now here I am trying to say, if Bob performs single shot measurement, then the entanglement will be broken. No.
Yeah.
You have to perform a global measurement. Am I missing something?
No, Mani. Here the measurement will be on this typical space of this share of qubits, no?
Yeah, that is true. That's what I'm saying. It is a global
and
measurement.
it would be rank of 2 to the power n s rho a, no?
Yes.
That's what I'm saying.
So
it is a global measurement. That's what I'm trying to say. It is not. Not on one copy,
It
one copy
cannot be
measurement.
rank one measurement. It cannot be rank one measurement for sure.
Not only rank one, it cannot be single shot measurement. That's what I'm trying to say.
Maybe it is not like product form.
It is not single shot measurement. To break the entanglement.
No, I think this is maybe I need to clarify. Maybe, you know, the question where you asked that you need to have entangled measurement. You always remember that even in when you have these sequences of quantum states, the typical, even let's say you have rho and it is diagonal, let's say in some psi I. So your typical strings, which are orthogonal to each other, but also product.
No. Ramama, let me rephrase my question. My question was, in practical scenario, so when many qubits are coming, no, I have to perform a global measurement. That I want to do. Because if single shot I do measurement, so because sending quantum information means if it is already correlated with some reference system, that correlation I have to keep intact. So single shot measurement, that will get broken, no. But in Shannon we can do by one sending.
Yes. So here essentially what I wanted to say is that you do a measurement on the typical subspace of A, where A has many copies.
Understand.
That's all.
I Okay. Any other question?
I think you know, Guruda, you kind of very pictorially gave this intuition of this packing lemma and covering lemma. Yeah. A little bit of elaboration would have really helped, because you need to have this, how the errors, essentially when you are packing, the error you may have because of this typical what you are considering. And
scenario, what should one tells that what they make for what they take for E, they add something epsilon. And here, when the question of discrimination comes, they subtract some epsilon to assure that they are indeed discriminable, and here, so that each state is properly covered. Are you asking this question?
This question as well as, because when you see this packing is more of like a coding, no, but only without destroying the coding.
Packing is more like a coding, and yeah, you are correct. And covering
so
is
in this coding also there will be some error. Then you teleport it perfectly fine. Then you decode it. That means you again go to this covering lemma. So in both cases there will be some kind of an error, no?
Yeah.
Which is obviously vanishing when you increase your n.
Yeah.
So, pictorially, physically, I would say that whatever you have said is fantastic. But if we can add this part also, then the people who will be working in this particular subject, because they have to deal with this error anyway.
Yeah.
That would be nicer. That's my point.
Any question from the students?
Yeah, any more question? If not, then we can end today's discussion here, and then again we will meet next week.
Yes.
Thank you,
next
Guruda.
week, same day, same time.
Thank you all for patient hearing.
Thank you, Guruda. It's really fantastic. Thank you so much, and thank you for organizing it also.
And I will correct the slides and send it.
Sure, sir. Okay, thank you. So I'm stop recording now and ending this call.
Okay.
Okay, thank you, sir.